In the last class, we were discussing the realization of a high order filter transfer function. This could be an arbitrary filter, but we've looked at so far, we've looked at all pole filters, which are and we've approximated the ideal brick wall by using the Butterworth polynomial. And we then realized that we can break up a high order polynomial into a product of first and second order terms. And I mean, if it's an odd order polynomial, then you'll have you can definitely have a first order term, and each one of these can be realized using individual building blocks, and the high order transfer function can be realized using simply a cascade of these sections. All right, and the first thing that we discussed yesterday was how do we go ahead and realize a first order section whose transfer function is 1 by 1 plus s over omega 1. Omega 1 corresponds to the 3 dB bandwidth of the first order section, and it's not merely enough to have an R and C and say okay, that also gives us a first order transfer function. One must realize that when we cascade sections together, loading does not affect the frequency response of the previous stage, right? And as we again were discussing yesterday, we use an op-amp and with negative feedback around it to realize a first order low pass filter, and the op-amp serves two purposes. One is that it facilitates cascading of stages easily because the output impedance of the stage is 0. So it can drive any load, at least in principle, without its transfer function getting modified, right? The second aspect that we saw yesterday is a practical one, namely that every capacitance, in fact even every resistance for that matter, there's always going to be a parasitic capacitance between those terminals and ground, okay? And it so happens that the transfer function in this case is not modified by parasitic capacitances on both plates of the capacitor or both terminals of the resistor, because in all cases the parasitic capacitance is either sitting at virtual ground, right, where the swing of the voltage swing across this capacitor CP1 is 0, simply because one terminal is real ground, the other terminal is virtual ground, and as long as the op-amp is ideal, CP1 has no role to play on the transfer function. Likewise, CP2, there is a voltage swing across CP2, but realize that CP2 is appears in parallel with the voltage output of the op-amp, and therefore all the current that goes into CP2 is being supplied by the op-amp. The voltage across the feedback branch, the RC circuit in parallel, is not modified, and therefore the output voltage remains the same. The transfer function remains the same. So this is an important practical aspect that is associated with such a structure. And as you can see, this filter structure, I mean, it's very simple, no doubt. It consists of R, C, and an active element, which is the op-amp. So these are often called active RC filters or Opamp-RC filters. All right, and so that was what we were doing yesterday. Now the next job is to basically figure out how to realize the second order section. And remember, and as we said yesterday, well, we can draw our inspiration from any number of second order filters that we already know. For example, this is a simple structure that we have, we've seen in our earlier classes, right? The voltage output, as we all discussed yesterday, is a band pass output. If you want a low pass output, what would you do? The inductor current has a low pass response. Now the question is, again, we'd like to make sure that this section, right, basically does not load, is not affected by loading of the next stage. So we'd like to have zero output impedance, and a straightforward way of doing that is to avoid loading, is to say, okay, well, R and this is L, right? And we must somehow figure out a way of tapping off the current through the L. All right. What comment can we make about? So this is IN. Let's say. What comment can we make about this voltage transfer function? This is. Remember all that in the circuit on the left, this current is flowing through the RLC network. The circuit on the right, also the current is flowing through the RLC network. So the voltage across the RLC network, which is band pass, right, that will now appear across the op-amp, except now that the op-amp is able to drive, any load, at least in principle. So this is the band pass out. But there's another problem. We hope that we'll be able to kind of somehow tap off that inductor current in some way. But there's a more fundamental problem with RLC filters, and what do you think that problem might be? Or rather, I would say a more fundamental practical problem with RLC filters, and what do you think that might be? The inductor, right? And all of you have taken enough physics classes to know that inductors are big and bulky, and they become bigger and bulkier when the frequencies involved are small, correct? Because remember that the resonant frequency of this LC network is 1 over square root of LC radians per second, and therefore if you want a low frequency, right, what do you call a low frequency pole pair, which is what you would need if you had a low pass filter with a low cutoff frequency, right? For example, you wanted to filter voice before it went into an A to D converter, and you would need bandwidths in the kilohertz range, right? And the L and the C values, either one or both would become so large so as to be completely impractical, right? So inductors, therefore, the problem is that inductors are bulky and expensive, right? And therefore, are not suitable in a whole lot of applications that target frequencies that are small. So now the question is, is it possible to achieve the same functionality without the explicit use of an inductor? All right, and the idea is the following: what is the current that's flowing through the inductor in terms of VBP? What is the current that's flowing through the inductor? VBP of S by Sl. Correct? So, in the time domain, what does this correspond to? Integration. So, I'd like to kind of draw your attention to the following, right? In an inductor, the current is, how is the current related to the voltage across the inductor? How is IL related to VL? 1 by L integral VL dt, right? What about a capacitor? Vc equals 1 over C integral IC dt. So, you can see that whether it's the inductor or the capacitor, both of them are performing the mathematical operation of integration, correct? The inductor, however, integrates voltage and generates a current, right? In the capacitor integrates current and generates a voltage, okay? So, basically, we want to replace an inductor. An inductor is an integrator, right? So, whatever you do, there must be some integration in that box. So, let's say you put a magic box here, right, whose job is to do the same thing as a physical inductor without using one, right? What mathematical operation must be going on in that box? There must be integration inside that box, right? We only know two types of two elements which are integrators in some way. One of them is the inductor, the other is the capacitor, right? We are already saying that we do not want to use the inductor, right? So, whatever you do inside, there must be a capacitor. Does this make sense? Right? So, in other words, if we are supposed to get rid of this inductor, right, with basically a black box, a magic box, let's say, well, its job is to look at VBP, correct? And what should it do? It should generate a current which is VBP over S times L, okay? And it should do it without using an inductor. I mean, I can't say the magic box and then inside I have another inductor. That doesn't make sense, correct? And we need only one integration. So, in principle, what do you think must be there inside that magic box? There must be at least one capacitor. Does it make sense? Alright. But unfortunately, this capacitor is a great integrator. However, it integrates current and generates a voltage. But what do we want? We want to integrate. Remember that this quantity here is an integral of, it's a current which is an integral of the voltage, right? But our man inside can only integrate. We need to integrate a voltage and generate a current which is the integral of the voltage. Our man inside can only integrate a current and generate a voltage, right? So, what do you think we should do? What do you think we can do? Convert voltage into current, right? Okay. Integrate that current, because the capacitor, our friend inside, can only integrate a current. So, you get a voltage which is now an integral of the current, right? And then what do you do? But what you are looking for is a current. So, but you have a voltage. What do? You convert a current back into, a voltage back into, that's the principle, right? Okay. And this can be done in many ways, and you already know how to convert a voltage into a current. And what do you think that is? Well, as I said, you've seen this before. right? We want, you've seen, so this is our friend, the capacitor inside, right? So let's call this R. Again, there's no need for this R to be the same as that R, but I just chose that way. Okay. So what is the output voltage here? Minus VBP by. So how are we converting VBP into a voltage, into a current? That resistor R in red is basically converting voltage into a current, and that current is flowing into the capacitor. So the output voltage is therefore an integral of the input voltage by, and is related through RCS. Okay. All right. But we have a small problem now. What is that problem? We want that negative sign is a problem. We want the integral of VBP, not the inverted version. So, well, if you want to get rid of a negative sign, what do? And you want to have an inverting amplifier with a gain -1. So, do you know how to do that? We know how to do that. What do you suggest that we do? Okay, well, this is R and this is R. So this is VBP over SCR. Correct? So we now have that all important VB by S term. Correct? But we have a voltage now. We need to convert it into a current. So what do? This current must be we need a current which is VBP by SL. Right? We have a voltage. So what do you suggest? How do we get from VBP by SCR to a current which is VBP over SL? Pardon? And what is the intuition? Well, we know that this potential is, what is that potential? That's 0, right? So simply converting a voltage into current is straightforward. We just simply put a resistor here. All right, and so therefore, what is the current that flows here? VBP of S divided by SCR square. All right. So this magic box in red is therefore doing the job of an inductor. Correct? And what is the equivalent inductance? All right. Okay. So so what does this correspond to? It's a voltage, all right. But in the original circuit, I mean, this this corresponds to, what does that current correspond to? It's the current through the inductor, correct? Okay, and VBP by SCR is, it's a voltage, which is proportional to, which is related to the current through the inductor by a multiplication factor R. Correct? So this voltage is a proxy for the inductor current. Correct? Because if you know this voltage, the current is simply this divided by R. Okay? Alright? And we wanted a low pass filter And what was the idea behind the low pass filter? The low pass filter was the inductor current. All right. So if we simply tap this voltage off, what does that correspond to? It's a voltage which is low pass. Does it make sense, people? All right. So, and the last thing is that we'd like to have voltage input, voltage output. So, if you wanted the input to be a voltage but not a current, what do you think you can do? Well, that's straightforward. Basically say, oh well, this is R and this is yeah. Okay. So, this is an example of, so this basically represents a second order low pass filter at this node. Okay, and the way it's drawn in the textbooks. I mean, can you comment on the order of the integration and the inversion? Can it be interchanged, or need it be the same, or what? It can be interchanged, and the way it's drawn in the textbooks is simply and I just, again, as I said, there's no reason for this capacitor, the two capacitors to be the same. There's no reason for all the resistors to be the same, right? In fact, there must at least be how many independent parameters are there in the second order low pass filter section? Omega naught and Q, right? So obviously, there must be another factor here which is independently variable, and that is it turns out to be that resistor there. And as we will see, simply making that QR, it turns out, and I leave this as homework, results in a transfer function here, which is, so let's say this is Vi and this is Vo. So Vo by Vi of S is nothing but, what is the DC gain? How do you figure out what the DC gain is? Let's say this, you are looking at the circuit for the very first time, right? I am only interested in the DC gain. Okay. One way to find out is to go and solve the entire transfer function and put S equal to 0, right? I mean, that's kind of a silly way of doing it, because if I'm only interested in the DC gain, it does not make sense to find the whole transfer function, put in all that effort, and then put S equal to 0 and throw away most of that information that you have, correct? So if you are only interested in the DC gain, you should be able to do it simply staring at this circuit. And so what? How do you think we'll do it? At DC, what happens? All capacitors are open. So this capacitor, both these capacitors are open. All right. So if I have a DC voltage, say 1 volt here, right? The current that's flowing here is what? 1 by R. And where must all that current flow? Pardon? It must flow into, nothing can flow through the capacitor, correct? It can only flow through QR and R. We don't know how much flows through R and how much flows through QR. Alright, but is there a way of finding out how much flows through QR? We look forward. What is the current flowing through this capacitor at DC? 0. If this current is 0 on average, what comment can you make about this voltage on average? What is the DC value of that voltage? 0. If this DC voltage is 0, what comment can you make about that DC voltage? Yes? Oh, this is simply an inverting amplifier, so that is 0, right? If that is 0, and what is this voltage? 0. So what is the current flowing through the QR resistor? 0, right? So all this 1 by R current therefore flows through which resistor? The feedback resistor on the top. So that's 1 by R. So if you put 1 volt here, what is the output voltage at DC? Minus 1. So what is the DC gain? Minus 1. Divided by 1 plus S by omega naught Q plus S square by omega naught square. Okay. And what is the expression for omega naught? Remember, this whole box here, what was it trying to do? It is trying to emulate the functionality of an inductor. And what is the value of that inductance? Right? Value of the inductance, and that is nothing but CR square. So omega naught is the resonant frequency of that LCR network that we had earlier, and therefore that's 1 over square root inductance times capacitance. The inductance is CR square, the capacitance is C, so this is simply nothing but 1 over RC. Alright? Okay. What about Q? How do we establish the quality factor of the tank? The quality factor, remember, for an RLC in a parallel network is nothing but
R divided by root L by C.
Very good. It's R divided by square root of L by C. And a good way of remembering this is that, quality factor basically quantifies, the amount of loss in the LCR network, right? So will you lose a lot of energy when R is high or when R is low in a parallel RLC tank? Ideally, when R tends to infinity, you have no loss, and therefore the quality must tend to infinity. So in the parallel RLC network, a good way of remembering the formula for Q is R divided by Q is dimensionless, so it must be a ratio of like quantities. If R is on the numerator, the denominator must have something of dimensions of impedance or resistance, and that is simply square root of L by C, right, which you have no doubt seen in your EM classes when you are studying transmission lines. So Q is R divided by square root of L by C. In a series RLC network, Q is square root of L by C divided by R, right? In a series RLC network, if R tends to 0, then you have no loss, okay, and the quality tends to infinity. So here what do we see? What is that, the parallel resistor here is simply nothing but QR divided by, what is square root of L by C? L is nothing but R square C, and the C goes away, so this is nothing but R. So you can see that the quality factor of the tank is. Does it make sense, people?